plus 1. When the SVM outputs this score, it corresponds to a 20% chance that the label is actually plus 1. And the way you do that is you just fit a single W and a single bias, like a one-dimensional W and a single bias term to the output of the SVM, and then you actually can convert the uncalibrated f of x into a calibrated probability using logistic regression on a single input variable, which is just the output score of the SVM. Yeah.
What are the trade-offs of applying SVM and then logistical regression versus just like logistical regression?
That's a good question. So most people do this when the SVM. Okay, I shouldn't say most. One reason to do this is when the SVM just has much better accuracy than the logistic regression. But you still want the SVM, but you still want to interpret the SVM's predictions as probabilities, right? This is a monotonic transformation of the data, so it won't decrease the accuracy of the classification, right? Because there's some threshold by which you predict positive and stuff rather than negative, and since it's a monotonic transformation, it will preserve the accuracy of the SVM, right? And so when an SVM, for whatever reason, and it doesn't have to be an SVM, it could be some other model, predicts, it just has much better accuracy than just using logistic regression directly, and you still want calibrated probabilities, then you use this approach. That's one reason too.
How do you test like whether better accuracy?
You train both. You have a validation set. This is the stuff that we've talked about the last few lectures. Right. You have two different model classes, in which case the model class is maybe specified by the loss function. Or two different model class comma loss function pairs. One SVM, one log, logistic regression. You train, evaluate on the validation set, see that the SVM gets much better accuracy. You say, let's stick with it, but I really want the probabilities to be calibrated, so let's fit one-dimensional logistic regression on top of the output of the SVM. Okay, so let's talk about the loss function that the logistic regression is actually optimizing for. So I talked about the sort of the probabilistic interpretation. So the loss function. So the loss function is, if you take this maximization problem, you can transform it into a minimization problem by taking the negative log of this term, and then by linearity of product and sum in terms of logarithms, it becomes like this. So now we're taking a minimization problem over this, and this is known as the log loss. Right? This is the loss function that an SVM is optimizing. The logistic regression optimizing. So these two give you the exact same answers. And now this is in a form that we've all seen. We just take the gradient of this, and we can solve using gradient set or stochastic gradient set. Any questions on this? Okay, so now let's compare log loss versus hinge loss, which is what SVM is optimizing for, right? So I plotted the log loss, which is this guy, where the target y is +1, and here's the hinge loss, and then here's their 1 loss. So this is what they look like. So one thing that sort of should stand out is that log loss is smooth, so it's completely differentiable everywhere, right? And what a hinge loss really pays attention to, sort of, is right here. Right? So it should, if you take this to the limit of the score being super negative, both become linear functions. So they both have the same behavior. They're both linear increasing in the limit of really, really poor predictions. As you make better and better predictions, the hinge loss actually decreases much sharper than the log loss does, right? And the log loss actually decreases very, very, very slowly. And so this is the regime where log loss and hinge loss really differ. Because if you're actually making a correct prediction with log loss, you're still incentivized to make even better, even more confident predictions, if your model permits that. Whereas the hinge loss has no incentive to do that. And so this effect sometimes leads to lower accuracy, but leads to more calibrated probabilities. Okay, so I'm just going to quickly go over the gradient derivation for one training example. You'll need this for the homework because you'll be implementing stochastic gradient descent for logistic regression in the homework. So we want to take the gradient of a single training example, log loss of a single training example. The probability is defined as this term, and I'm just going to go over this quickly. You could review this at your leisure outside of class. You take the log, you split the terms, it looks like this. This is a linear model, so it just looks like this. Then you take the gradient of this, and the gradient of this is 1 over log of this. The gradient of log of something is 1 over it times the chain rule. And it looks like this, and then and it turns out that if you manipulate the numerator and denominator a little bit, you can re-express it as probabilities, and then you simplify to this. So if you carefully write down the derivations yourself and understand it, the actual gradient that you write down for gradient descent for logistic regression is actually a fairly simple rule. Right? And the interpretation is fairly simple too, right? It's like if you're really confident that the label is correct, then you make no update. If you're really confident in the wrong answer, then you make a big update, and then everything in between. Okay, so logistic regression, just to summarize. 2 interpretations. One is maximizing likelihood. One is minimizing log loss. And they're equivalent. Any questions on logistic regression? Yep.
So just in general, are there like natural generalizations of these things, like
Nonlinear models.
no, to like multiple, to like more than 2 classes? Because we only talked about binary classification.
Yes, there are. I'm trying to remember when. I do cover it. I forget exactly which lecture.
Okay.
I will cover.
Okay.
Okay. So now, next we're going to talk about feed-forward neural networks, which is the precursor to deep learning, which has been sort of a buzzword in machine learning these days. But they're, not quite. We'll talk about deep learning in greater depth towards the end of this class, towards the end of this course. So this is a one-layer neural network. It's also known as with a single sort of output node. It's known as a neuron. It's sort of a biologically inspired machine learning model. The basic idea is you take in a bunch of inputs, so you can think of one input per feature of your input vector x. This is just sort of the way people who think about neural networks think about the problem, but it's mathematically equivalent of having a feature vector of x's. We have weights on each of these sensory inputs, and we combine them, and we predict an output. This is a neuron, an artificial neuron. What is this function? Well, it's a linear function typically. Like it's you have a weight vector for each sensory input, and then you have a bias term, and then you output a score. So it's actually a linear model, and this output score typically has a S-shaped transform. So as the score gets really large, you have maximum activation. As the score gets really negative, you have 0 activations. So what does this look like? Anyone? I'm sorry. I'm sorry. It looks like a perceptron, yes. Especially if the transfer function is linear. If the transfer function is S-shaped, what else does it look like? This is really obvious. Don't doubt yourself. Good. Logistic regression. Right. A simple one-layer neural network with a sigmoid S-shaped transfer function is equivalent to logistic regression. And you don't need the sigmoid function. So you could also any type of in practice people use many different types of S-shaped curves or different types of transfer functions. There's the sigmoid, which is what we talk, which is equivalent to logistic regression. You could also use hyperbolic tangent. And then there's another one called rectilinear, which is not S-shaped, which we'll talk about when we cover deep learning in greater depth at the end of this course. But what makes a neural network, conceptually, when people think about building neural networks, they don't think about just one layer, they think about multiple layers of neural networks, right? And that's where they differ from things like logistic regressions and single perceptrons. So the reason why people want to use neural networks is not because you can just do one layer, it's because you can stack multiple layers. So here's one example. So we have, the x's are inputs, so the blue circles correspond to a vector of 3 inputs. And then each of these little nodes, so each of these nodes, so we have a hidden layer of 2 neurons that takes inputs and outputs some variable response. And then we have a second layer that takes as input the outputs of the 2 neurons in the hidden layer, and then finally outputs the answer. So this is the model class, right? It's a nonlinear model class. Turns out that this model class can approximate arbitrary functions, right? And so long as you have enough hidden layers, you can approximate arbitrary functions with this model class. You might need a lot of neurons in the hidden layer, but you can do it. And this was known, nowadays it's known as a fat 2-layer network because the hidden layer is very. In order for this model to actually approximate arbitrary nonlinear functions, the hidden layer needs to have many, many, many neurons. So how does this connect to what people these days call deep learning? Well, instead of having just 2 layers, which is what most people in neural networks used up until about 10 years ago, something like that, is you have many, many hidden layers, and each hidden layer is relatively narrow, right? So it's deep and narrow as opposed to shallow and fat. Why might we prefer a deep network over a shallow network? So it turns out that these deep networks are, given a fixed number of neurons, these deep networks are often more expressive than a similarly sized shallow network, right? In order to capture this function in a shallow network, it actually, it requires an exponentially large fat shallow model, because of all the different nonlinear transforms stacked on top of each other. The one question, and for those of you who have studied circuits in complexity, there's an analogy there as well. But is this easier to train than a shallow 2-layer network? So that's something we'll talk about later on in the course as well. So training neural networks, I'm going to train using stochastic gradient descent. Surprise, surprise. And you can even use gradient descent with some caveats for really deep neural networks as well. Let's just go for a simple example. So in this example of a 2-layer network, there are these parameters. Okay. So 3 weight vectors and 3 bias terms, corresponding to layer 1, first neuron in layer 1, second neuron in the neuron in layer 2. So keep in mind that each of these outputs is a S-shaped transfer over a linear scoring function. So let's say we want to minimize the loss of our prediction y, given the output of the top layer, and we want to take the gradient of this loss with respect to, is that W2? That's W2. So these weights right here. So then linear differentiability. This is just sigma 2. And the definition. So I take the derivative of the sigma function with respect to W. Sigma equals sigma of f of x. So we do this. And so that's what this looks like for training this layer. And again, you could rederive this following these steps at your leisure outside of class. So I'm going to go over it pretty quickly. And it gets a little bit more complicated for a lower level layer. So one of these weight vectors, because then you have to stack chain rule now. So you do the same thing in the beginning, but now you have to stack chain rule because it's this. You have to take the out because the way you get a gradient for this guy, it's fed as input to this guy. So when you differentiate this guy, then based on the weight of this guy, then you get the gradient of this guy. So this is called backpropagation. So people in the sort of the neural network community, when they invented this training algorithm, they called it backpropagation. Turns out to be equivalent to computing the gradient with chain rule. Any questions about neural networks? Okay, so I'm going to end the lecture today with a discussion over different evaluation metrics. So we've talked about 0-1 loss. We've talked for classification as sort of the measure of choice, at least for evaluation. So we're going to mostly focus on evaluation in this last part, not about how to minimize these loss functions, although I'll talk about it in a little bit. And we talked about squared loss as the measure of choice for regression. Is there anything else that we could possibly care about other than 0-1 loss and squared loss? Turns out that there is. So let's look at an example of cancer prediction, right? So we have this sort of table of sort of possibilities. Suppose our model predicts that the patient has cancer, and the patient in reality has cancer. Loss should be low, because we got the prediction correct. Suppose our model predicts that the patient has cancer, and the patient doesn't actually have cancer. We incur some loss, right? Because there's a cost to this type of misprediction. It's not the worst thing in the world. The worst thing in the world is, a model predicts that the patient does not have cancer, and the patient in fact does have cancer. This is like an extremely bad loss, right? And if we predict no cancer and the patient doesn't have cancer, there's lower zero loss, right? And so 0-1 loss is the case where this matrix of loss of cost is symmetric, right? 0, 1, 1, 0. That's 0-1 loss, right? It treats negative and positive. It treats negative. So this is like y equals +1, y equals -1, f of x positive, f of x negative, right? 0-1 loss, it says if the signs don't match, I incur a loss of 1. If the signs match, I incur a loss of 0. So it just treats this matrix as symmetric. There are many, many, many cases in the real world where you do not want to do that. And in particular, if let's say most people don't have cancer, but some people do, and for people who do have cancer, we really want to make sure that our model is correct for the people that do have cancer. So that's a very common scenario in practice. In those cases, we care much more about predicting the positives correctly than we do about the negatives. So this is known as a cost matrix, and 0-1 loss is a special case where the cost matrix is symmetric. So you could just put your own numbers in here. So how do you optimize for these types of cost matrices? There's no actually universally accepted way to do this. The reason being that each one requires a different. You could design your own surrogate loss functions that can optimize for this in different ways. Because this, again, it's a strict generalization of 0-1 loss. Therefore, it is also smooth. It also zero or discontinuous everywhere. You cannot directly optimize for it. So you have to design some sort of surrogate. And there's no commonly accepted way of doing this. I'm just presenting here the simplest way. And it would be the first thing I would try. And that's simply cost weighting, right? Suppose our cost matrix takes the following form, right? If the prediction is correct, the loss has to be 0. If the prediction is incorrect, it's some number that's not 0 but need not be symmetric. In this special case, you can simply just do cost-weighted prediction, right? We minimize the same loss function, except for examples where the true label is 1, the cost of mispredicting is 1,000 times greater than the cost of mispredicting when the true label is -1. Right? And this is just up to some scaling, just another instance of the kind of loss minimization we've been talking about in this class. And you can just derive the gradient and solve it. Okay, so accuracy is, and asymmetric 0-1 loss type concepts for accuracy is not the only way we can think of evaluation. Two other types of evaluation are precision and recall. So imagine that we have this table where there are, I believe, 125 patients in this test set, and our model, and in 25 of the patients in the test set, the patient has cancer, and in 100 of the patients in the test set, the patient does not have cancer. Our model then predicts has cancer for these and no cancer for these. So this is called also known as a confusion matrix. So these are called true positives. These are called false positives. These are called false negatives because our model predicts a negative, but it's actually not a negative, it's a positive. And these are called true negatives. So precision says the precision of our model is the number of true positives divided by the number of true positives plus the number of false positives. So it's this guy divided by this guy plus this guy. So it's this, we take this guy, we normalize by the sum of this row. What does that mean? That means of the patients that our model predicted as having cancer, how many of them did actually have cancer? Right. Recall is the true positive, this guy, divided by the number of true positives plus the number of false negatives. So this is the number of false negatives. So it's this guy divided by this column, the sum over this column. So it's saying, of the patients that actually do have cancer, how many did our model predict as having cancer? Right. So both these measures, these are two measures, both focus on this cell. They either normalize by this column or this row. They completely ignore this cell. Right. Because having cancer is, in this case, assumed to be the rare event. And when it happens, we want to really care that we get it. So we care more about the positive examples than the negative examples. And there's a notion called the F1 score, which is used by a lot of people in the community. And it's simply the harmonic mean between precision and recall. So if your model, how does harmonic mean work? If your model has perfect precision and zero, let's see. If your model has really high precision, really low recall, then the F1 score is going to be really low. If your model has really low precision and really high recall, the F1 score will also be low. The F1 score is only high if you have both relatively high precision and relatively high recall. So for example, for cancer, you might say, I'm willing to tolerate low precision if I have high recall. Right? If you have cancer, I definitely want to predict that you have cancer. It's okay if I have a bunch of false positives. So, people often plot, when they plot the performance of a model, they often plot what's known as a precision recall curve. So usually what happens is that the examples that the model is really confident about, like I'm really confident that this patient has cancer, it's true. So as you decrease how much recall you care about, precision goes up. And again, in the degenerate case where I just predict everyone has cancer, I have 100% recall, de facto, right? Because anyone who possibly had cancer has cancer. The precision is as low as possible, right? So usually you have this trade-off curve that looks like this, and a model that has a trade-off, precision recall trade-off curve that is as closer to the top right corner is better. Okay, let's think about another example. Imagine that we're, instead of predicting something, instead of classifying something as positive or negative, we're just returning a ranking, right? This is something that we often use these models for, right? We don't necessarily care about the score you give it. We don't want to just look at the top 10 most confident, most positively scored examples. Like oftentimes when we use a machine learning algorithm to score something, we don't have time to look at everything. We only have time to look at the top 10, right? So we use a model, score stuff, rank it by the score, look at the top 10. This is what happens to search engines like Google, recommender systems. They do this all the time. They have some score about the quality of some result, search result or recommendation, and they give you a ranking ranked by that scoring function. So, for example, and so what that means is now we wanted to find evaluation measures over rankings and not over individual examples. So classically what they do is, you have some scoring function f, maybe it's a linear model. Users only look at the top 4, so we take all the possible search results from this query, we sort by the scoring function, and that's what we show, and it's a users only look at the top 4. And let's suppose that the user actually found this result interesting, and the user would have found this result interesting had he looked at it, he or she looked at it, but he didn't. So one evaluation metric that captures this effect is called precision at 4, right? So precision at 4 basically says, let's just look at the top 4 results and measure what fraction of those are positive examples. So in this particular case, the precision at 4 is 1/2. So precision at 4 says, given any scoring function, give me a ranking, and I'm only going to look at the top 4 and measure the fraction of positive examples. Anything below the top 4, I completely ignore. There's also recall at 4. So recall at 4 says, let's look at the top 4 results, and what is the fraction of the relevant result that I captured in the top 4? And if there are 3 relevant results and 2 of them are in the top 4, the recall at 4 is 2/3. Any questions? Yeah.
If you have a lot of pages that are relevant, then wouldn't the recall score be?
That is correct. So in practice, people don't usually look at recall. Specifically in the context of like ranking thousands of results, when you only look at the top 10, people typically only look at things like precision. They don't look at the recall. This is just for math completeness. I'm just presenting. There's another, the final set of measures, ranking measures I'll talk about are based on things like pairwise preferences. So in the method of pairwise preferences, I'll imagine that there's one positive result and a bunch of negative results in the simple example. Then pairwise preferences says, let's look at all pairings of positive negative pairs. In this case, there's, there's 6 negative results and 1 positive result, so there's 6 pairings. And I want a ranking that ranks as many positive examples above negative examples as possible. So in this particular case, this positive example is ranked below 2 negative examples and ranked above 4 negative examples. There are 2 pairwise disagreements and 4 pairwise agreements. And this concept leads to another ranking measure that's very often used in practice to evaluate these types of models, and it's called the ROC-Area. For those of you curious, ROC stands for Receiver Operating Characteristic. I forget why it's called that. You could look it up, I'll give you the history. And so the ROC-Area is the true positive rate, also called the sensitivity, and the false positive rate, that's the curve. So the ROC-Area is basically the area under this curve. And it turns out the ROC-Area is mathematically equivalent to the fraction of pairwise agreements. So here's an example. Suppose I had a ranking over 5 instances, of which 3 are positive and 2 are negative. The number of pairwise preferences is 6, because there's because it's a number of positive negative pairs, so it's 3 times 2, it's 6. And of the 6 preferences, we see that the agreements are, so this positive example is ranked above these 2, so it's 2 agreements. This example is ranked above 1 negative example, so that's 1 more. And this example is now ranked above any negative example, so it's 0. So the number of pairwise agreements is 3. The total number of pairwise preferences is 6. The ROC-Area is 50%. And you want the ROC-Area to be as close to 1 as possible. The ROC-Area gives you, the ranking that gives you ROC-Area at exactly 1 is the one that ranks all the positive examples above all the negative examples. The final measure we'll talk about today is called average precision. Average precision is the precision recall curve. So we've already talked about precision, I want to talk about recall. And what it basically says is as I vary, so the way these curves are predicted often is they vary the ranking of the top k. So as I look at the, so I sort by the scoring function of my model, and I look at the ranking of the top k, and then I compute the precision, compute the recall, and then I average that. That's what average precision, or excuse me, I compute the precision, and I average that. And that's the precision recall, that's the average precision metric. So here's how it looks. I get the same ranking. In this ranking, there are 3 positive examples at rank 1, rank 3, and rank 5. Average precision is the average of the precision of this ranking at rank 1, at rank 3, and rank 5. So at rank 1, the precision is 100%. At rank 3, the precision is 2/3. And at rank 5, the precision is 3/5. And the average of that is about 0.76. So that's average precision. So if you read machine learning papers that talk about which model they chose and why, they often say we chose this model because it has the highest average precision or the highest ROC-Area or the highest precision at 10. And and a lot of that time is dependent on sort of what is the use case of your model. So how do we think about comparing ROC-Area versus average precision? ROC-Area cares about every pairwise preference equally. Our average precision cares more about the top of the ranking. And to illustrate that point, let's look at these 2 rankings of 3 positive results and 2 negative results. Both of these have 6 pairwise preferences for ROC-Area. In both of them has an ROC-Area of, okay, I made a mistake here, but both of them are supposed to have an ROC-Area of 0.5. But the average precision is much higher for this guy because it ranks the positive result at rank 1, which matters a lot here. Okay, these 2 are supposed to be flipped. I'll fix this before I release. I'll fix this example. I made a mistake. Okay, so just to summarize. Even though in terms of learning algorithms, the actual objective function that people traditionally think about is often based on things related to classification of a single example or regression of a single example, there are many different ways that people use these machine learning algorithms in practice. And what that means is they may lead to different evaluation metrics that you might want to use during validation for model selection, right? And so these are based on different scenarios, such as you may have cost-sensitive predictions. And oftentimes the positive class is rare, in which case you want to focus more on the positive class in your evaluation measure. So you want to use things like precision at 10, ROC-Area, things like that. And so this has been sort of a large body of work in, for example, in the search community, like people who build search engines. They try to figure out how to train these models that score, that gets the top results accurate, and don't necessarily care about whether or not it gets the 50th result classified accurately. Okay, any questions on evaluation measures? Okay, so next lecture we're going to talk a lot about regularization, different ways of regularizing, including the L1 regularization will lead to something called a lasso, and also this upcoming Thursday evening, recitation on matrix linear algebra.